In this video, we're going to look at the Big Bang Theory and some of the evidence we have for it. If we go back about, well, just over 100 years ago, people weren't sure if our galaxy, the Milky Way, which is our, 100 billion nearest stars, was all there was to the universe. We could see those stars with our naked eye. We could see a lot more with telescopes. But using the telescopes we had back then, we could see these little splodges of light in the night sky, and we weren't too sure where they were. Were they part of our galaxy? And if they were, what were they? Were they types of comet or something like that? Um, or were they much further away? And in about the 1900s, they were able to turn telescopes to the sky, measure the distance that these things are away, and what we discovered was they are way, way further away than our galaxy. So you kind of have our galaxy as our little local village or cluster of stars, and then a big distance where there's absolutely nothing. I mean, there's a reason why space is called space. Nothing, 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 and then another little village of stars. More powerful telescopes these days, so this is taken by the Hubble Space Telescope. If you look at the image here, each of those dots of light looks like a star. It's not. Each of those is a galaxy. We believe there are 100 billion galaxies, and in each of those little splodges of light, that is 100 billion stars in itself. Now, a scientist called Hubble then decided, okay, well, let's see what everything's made of in our universe. You might think, okay, well, we'll have to go there to find that out, but we actually don't. And you've come across this before. So you did flame tests in year 8, and you could tell by the colors of the flames what elements were present. And we can actually do that with stars as well. So Hubble used a telescope, looked at our star, the sun, put the light that came from it through a kind of prism, and what you get is this. You get it spread into its spectrum, but you get little lines, dark lines in it of light that has been absorbed by the elements that kind of surround the sun, and they're very distinctive. And we can test elements on Earth and get those same lines. So we might know that, say, this line, and these two lines here are from hydrogen. This line here is from chlorine, maybe this one as well, and so on. And we can identify the elements and make those up. And so we know that our star, the sun, is made up of the same elements we have on planet Earth, mainly hydrogen, helium, and a few other elements. We turn that telescope to another star in our galaxy, we get exactly the same picture. So even of things that are, hundreds, thousands of light years away, we can tell what they're made of. And what Hubble discovered was every single star in our galaxy, the same pattern, made of exactly the same things. He then turned it on stars in other galaxies, and he got a surprising result, because when he looked at another galaxy, he noticed you get exactly the same pattern of lines that you would for a star in our galaxy. The only difference is those lines are all moved towards the red end of the spectrum. Okay, so remember red, I mean, you can see it, it's up here. So the line that should have been here is now moved towards the red end of the spectrum. Likewise, this little double line down here moved up more towards the red end of the spectrum. This one that's in the middle of yellow is moving up more towards orange. Okay, so what we say is that the light has been red shifted. He said, okay, that's quite strange. Let's see about other galaxies. Point at another galaxy, red shifted. Another galaxy, red shifted. Every single galaxy he pointed his telescope at, the light was red shifted. And in fact, he was able to measure how far away those galaxies were. And what he discovered was the further away galaxies are, the more red shifted the light is. This movement of these lines towards the red end of the spectrum is more pronounced in galaxies that are further away. And we had an explanation as to what causes this redshift, because it was already a scientific theory that had been produced years earlier, and it's called the Doppler effect. And it works for all types of waves. So if the source of a wave is coming towards you, you will perceive that wave as being of a higher frequency. And as the source of the wave moves away from you, it will be a lower frequency. And you hear that as a car drives by, because the car engine will produce a single note, but it doesn't sound like that to you. It will sound something like, apologies for this, meow, Okay, so you can see it's higher pitched at the start as the car is coming towards you. And as it moves further away, then as it passes you, moves further away, it gets lower shifted. Now, in this case, we can see here that the light is shifted towards the red end of the spectrum. And if you remember from your electromagnetic spectrum, red is more towards the lower frequency. Okay, so if these are shifted more down this way, that would mean that the light was blue shifted, and it would mean we perceive it at a higher frequency, but all the light from the galaxies was perceived to be at a lower frequency, which means the light, or the galaxy that's producing that light, is moving away from us. So Hubble and other scientists then were able to say, okay, so if this is our galaxy and we have another galaxy over here, it's moving away from us. Another galaxy over here, it's moving away from us. And this other little spiral galaxy, it's moving away from us. This one over here, it's moving away from us. And in fact, you actually get a straight line graph that if a galaxy is further away, so let's say we have another galaxy over here, it'd be moving twice as fast. So if we have another galaxy twice as far away as this one, it'd be moving away from us, but twice as fast. And you might think, well, that means everything's moving away from us. Why do people not like us? You know, why is everything moving away from us? Or maybe you might even think, oh, well, we're the center and everything's moving away. But it's not true. No matter where you are, you can kind of say it's a little bit akin to if you got a balloon and drew the galaxies on it, and then you blew up that balloon to make it bigger. Let's see if I can do this. What you would perceive would be all those galaxies move further away from each other. Okay, so if you pick our galaxy, the first one I drew there, this one here, they will all move further away from it. But no matter what galaxy you're in, everything will perceive the same. They will all see that the galaxies are getting further away. So what we tend to say is that space is expanding. Now, if we go back to this from our viewpoint, what we say is, okay, all the galaxies are moving further away from us, which means in the future, galaxies will be spaced further apart. Makes sense. However, if we then rewind time and we go backwards, what we see is the galaxies would get closer and closer together. And there would be some time in the past where if we went back in time, this galaxy would be on top of us. And in fact, every galaxy that's that same distance away is moving at the same speed. So in fact, all those galaxies would be on top of us at the same time in the past. Meanwhile, this galaxy here is twice as far away as this one, but it's moving twice as fast. So in fact, it would take it the same amount of time if we went backwards to be on top of us. And that's true for all the galaxies. So if we rewind time, because we have this evidence that the galaxies are moving further apart, therefore, at some point in the past, they would all be together. And that's where the Big Bang comes from. So the red shift that Hubble observed from other galaxies is evidence for the Big Bang. But what the Big Bang theory says is somewhere between about 12 to 15 years ago, I think it's about 13.8 billion years is the current estimate. All the mass, energy, everything that ever existed in the universe was in a tiny point called a singularity. And it sprung forth from that in a massive expansion. Now, and it's been expanding ever since and will continue to expand. But as things expand, they cool, which means just after the Big Bang, it would have been very, very hot. And by hot, we mean everything moves fast. However, as it expands, it cools down, and eventually it cools down enough for things like neutrons and protons to form from quarks. After 3 minutes, it cools down enough that the protons and neutrons are moving slow enough that they can combine and form nuclei. After about another 300,000 years, it's cooled down enough that electrons that were produced are then moving slowly enough that they can be captured by the nuclei and form atoms. And then we have essentially just this big cloud of hydrogen gas. And then you know from before, then gravity acts on that, forms stars and solar systems and planets. Okay. The way in which this term here, nucleosynthesis, which is just how all the nuclei were generated by the Big Bang, our theories match with the amount of hydrogen, helium, lithium, beryllium we see in the universe. matches with what the Big Bang Theory suggests. Okay, so Big Bang Theory is where all the universe sprang forth from a tiny point called singularity about 13.8 billion years ago. Redshift is an evidence for that because it tells us that galaxies at the minute are moving away from us by the Doppler effect, and therefore at some point in the past must have been together. Okay, we'll look at another piece of evidence for the Big Bang Theory in the next video.